Hi, I'm Bill Bartee, part of the main sequence team. And today what I'd like to do is speak to you about an exciting new field called quantum computing and quantum sensing. Now, while there's a ways to go, quantum computing could eventually change the world. It could transform chemistry, speed up drug development, make communications more secure, and turbocharge artificial intelligence. But to really understand what a quantum computer is all about and how it works, let's first talk about something that we use and are familiar with every day, classical computers. Now, everybody is familiar with a classical computer. We navigate our way through cities using GPS systems. We make calls on our smartphones. We type out memos on our laptops. And we've even heard of these things called supercomputers, which are these very large, powerful systems that are often the size of tennis courts and do all kinds of things like weather forecasting. That's classical computing to a T. But what's often not talked about is that classical computers have limitations on what they can do and do well. There are certain problems that they're not good at all. Those problems often are optimization, chemistry, simulation. All of these things are very, very important in daily life, and they're also very important problems to solve. So realizing that classical computers have limitations, the person on your screen, Richard Feynman, proposed that physicists build a quantum computer because he said that, after all, nature is quantum, so we better build one. And this was in 1980. And then in 1994, another professor, Peter Shor, came up with something called Shor's algorithm. And this was a polynomial time algorithm that could be used on a quantum computer for integer factorization. Now, informally, what it does is it says that, look, given an integer, what are its prime factors? And being able to take an integer and find its prime factors, especially if it's a very, very large number, is a daunting task. But with Shor's algorithm, Peter showed that you could do this fairly easily on a quantum computer. That suddenly got lots of people's attention because the entire internet and the entire security of the internet is built on primes and prime factorization. So that sort of brought the field into the attention of lots of people worldwide. Now, the thing that makes a quantum computer potentially much more powerful than a classical one is it's got a much, much larger computing space due to its architecture. It's built on something called qubits instead of bits as their computing units. And it also has two properties called superposition and entanglement, which we won't talk about here, but are part of the makeup of a quantum computer. So to understand the difference in computing space, let's look at the sphere on the left. And you see that there's an arrow that points up or down. So a bit can be a 0 or a 1. It can be on or off, or it can point north or south. In juxtaposition to that, a quantum computer, its compute space could be anywhere on the globe. So you can see that having 2 points on the globe is very, very different from having an infinite number of points on the globe. And that's the difference in compute space. It's much larger in a quantum computer. So what can you actually use a quantum computer for? Well, because of this large computing space, quantum computers could be as revolutionary as the digital electronics revolution. They're very good at optimization, really good at simulation and probability, and also excellent at security problems. Now, as an example, let's just talk about simulation of molecules. So a simple caffeine molecule, which has about 24 atoms in its structure, and which makes up the coffee that we drink, some of us drink every day, it can't be simulated on the world's largest supercomputer. And you might ask why, because 24 is a pretty small number. Well, the reason is because you have to simulate every electron to electron repulsion, every electron to nucleus attraction, and every other kind of interaction that these atoms are having with one another. And that becomes an extremely large number. So the largest supercomputer in the world cannot do it. Well, if you have a quantum computer with somewhere around a couple of hundred logical qubits, it could do it fairly simply. So imagine what this could mean. This could mean that we could revolutionize the chemistry, the drug, and the material fertilizers, especially if we could simulate all these molecules. And even in today's situation where we have a pandemic, this might mean that we could speed up drug development for a vaccine or some other medicine to help those who get some sort of COVID or whatever the pandemic of the day is. Quantum computers can also help to optimize things. So if you are a money manager and you run a big portfolio of stocks and you want to analyze every risk and every return possibility, well, that's something that a quantum computer could do, and also do it fairly easily. The other thing a quantum computer can do is it can improve the security of the internet, because it can analyze and understand all of the potential threats that a hacker could have. Now, what may surprise you is that Australia is a leader globally in quantum computing. And this came about because there were a couple of professors here 20 years ago who actually became very interested in quantum computing and got some dollars and some funding from the university sector as well as some of the government sector. And this started the revolution, or the building of the expertise in this country. So one of the professors, Bob Clark, was over at UNSW, and there was another professor at ANU. And from all of this funding into quantum physics and quantum mechanics, Australia has, over the years, built up a significant expertise and a significant critical mass in this area. And there's lots of efforts in quantum computing going on today at most of the major universities. UNSW has a very big effort, as does the University of Sydney, ANU, University of Melbourne, and many of the other universities, UTS, Swinburne, all these universities, University of Queensland, they all have big efforts in quantum computing, whether it's computing or algorithms or error correction. There's lots of expertise in Australia. And when we at Main Sequence were looking to invest in this particular area, what we did was we looked around and we found that one of the common problems with quantum computing is errors. That the quantum computers that are built today are very subject and very prone to having a lot of errors. And this, having errors, is a big problem. So we located Professor Michael Biersuk, who is shown on the screen here, and he was building a company, or was thinking about building a company, which eventually became Q-Control. We helped him to form the company and spin it out of the University of Sydney. And what Q-Control does is it has a set of software that's based upon proven techniques in his lab to suppress errors in quantum computers. And if you can suppress errors in quantum computers, that means that you give them a lot more time to compute. And in more time to compute means you can run a lot more gate operations and solve much bigger problems. So we invested in Michael's company, Q-Control, and he now has the leading quantum suppression error control company in the world. Now on the screen right now is a list, a partial list, not the whole list, of people, universities, countries who are invested very heavily in this particular field. So you can see that at the top, there's lots of countries who are interested in quantum computing. In the second slice, you'll see there are companies like Lockheed Martin and Google and Amazon and Hitachi and Microsoft and Intel, and the list goes on and on, Alibaba. And in the middle, what you see is a number of startups. So Silicon Quantum Computing out of the University of New South Wales, Quantum Brilliance out of ANU, Q-Control out of the University of Sydney, Quintessence Labs out of the ANU, Psi Quantum, which is in San Francisco and has a Australian as its founder. These are all, this is about a small number of startups who are in the quantum computing field. And then at the bottom, there's a list of universities that are also interested in this particular field. So essentially what this demonstrates is that there's billions and billions of dollars and lots of entrepreneurs who are interested in the field and believe that quantum computing can be the most important thing in computing this century. We also are believers of that. So one of the things that we are challenging Australia with is we have a critical mass of talent, we have leading universities, and we have an emerging quantum computing startup sector. Essentially, we have a lead position in the world in this field, and what are we going to do with it? Well, Kathy Foley over at CSIRO built out a quantum roadmap. She took a look at this, and what she said was that, look, by 2040, we could have an industry here in Australia that's generating $4 billion of revenue, and it could produce 16,000 new jobs. Now, that's a substantial number. But what that doesn't include is that doesn't include all of the impact that it could have on drug discovery and improving chemistry and optimization of portfolios. So you can see that this field of quantum computing, not only is it exciting in its own right, but it will have major impact on other industries. And so what we'd like to do, and what we at Main Sequence are dedicated to doing, is helping to preserve and protect and even advance the lead that some of the companies in Australia have. We hope you find this as exciting as we do, and we hope that you can support the field, and let's build an industry in the quantum computing area and quantum sensing area for Australia. Thanks for listening, and hope to hear from you soon.